Okay. So, a system of equations. This is going to be a very short unit. We'll probably test on this like next Friday. So, wait, what day is today? Wednesday? Yeah, next Friday. So like, I think. I don't know. It's really short is what I'm trying to say. And today's lesson is going to be really easy. A set or two or more equations with the same variables is called a system of equations. A system of equations. Could be two equations, could be three. And like we saw in the warm-up, right, we had two linear equations. That was a system. And the solution to that system is where the two lines cross or intersect. What does intersect mean? To cross, right? So if they're crossing at a certain point, like we saw 1, 1, that's the solution to that system. It's the only point in which those two linear functions are ever going to cross. So let's take a look at this system here. You're going to know it's a system. Sometimes it'll have this little squiggle parentheses. Sometimes it won't. Okay, Aaron, let's keep our shoes on. Sometimes it'll have a squiggle parentheses. Sometimes it won't. But that tells me this is a system. These are two equations that work together. Okay? So the y in the first equation is the same y as the y in the second equation. And the x is the same x. Okay? Right away, do you guys notice anything interesting about these two lines? Maybe something we learned in the last unit. Liana, what do you notice?
They're perpendicular.
They're perpendicular. Alex, is that what you were going to say? Okay, Alex, how do we know they're perpendicular?
Because the second equation has the fraction flipped and it is the inverse operation.
Okay, good. Let's take a look. Liana, what's my first equation? We'll call it equation A. What's my what's my slope for equation A?
-2.
-2. Okay. And for equation B, what's my slope for equation B? 1/2. So -2 and 1/2, hopefully we can recognize right away, those are perpendicular slopes because they're inverse reciprocals. Negative and a positive, 2/1, 1/2. Give me a thumbs up if you see that. Okay. So what we should see when we graph these is two lines that intersect at a right angle. How many degrees is a right angle?
90 degrees.
90. All right. Now we're not always going to have perpendicular lines. Were our lines perpendicular in the warm-up?
Yes. No, because they're not 90 degrees.
Did those look like 90-degree angles all around? No.
That's a cute.
Were my slopes inverse reciprocals? No. But we still had a solution, right? So they don't have to be perpendicular. I just wanted to check back and see if you guys could recognize that. So now we're going to graph these. This is just like the warm-up. Let's take a look at the orange equation first. What's my y-intercept for equation A? 3. So I'm going to make a point at 3. What's my rise over run? -2/1. So what direction am I rising? Down. And I'm running to the right. Down 2, right 1, dot. Down 2, right 1, dot. And remember, because we're looking for an intersection point, we want as many points on this line defined as we possibly can. With our rulers, we're going to make a nice straight line through all 6 of those points. And we're going to label this line with the letter A. It's my first line, my first linear equation. It'll get the letter A. me a thumbs up if you're with me so far. Good. Half of us are with me. My second slope is 1/2. What's my second y-intercept?
-2.
-2. So I'm going to begin by making a dot at -2. I'm going to rise 1 up or down? Up because it's positive, and I'm going to run 2 to the right because I always run to the right. So from that beginning point, I'm going to rise 1, run 2, boom. Rise 1, run 2, boom. Keep going all the way up. Keep going all the way down. Thank you. And then your note sheet is on your desk, okay? Okay, this blue line now, we're going to label it with a lowercase b. We always want to label our lines with lowercase letters. Points get uppercase letters, but lines get lowercase. Lowercase lines. Do you guys see where those two lines intersect?
Yeah.
Yeah? What are the coordinates of my intersecting point?
2,
2, comma, -1. Okay, go ahead and circle your intersection point just like that. And our solution to this is to -1. Do these lines look perpendicular to you? Yeah.
Yeah.
If we had a protractor, we could measure it, but we're not going to go that far. Doesn't matter. All right. Up, down, sideways, thumbs. How are we feeling about that? Thumbs up seems doable. Seems easy enough. Thumbs sideways, a little tricky, a little confusing. Okay. It's not too bad, right? It's basically what we've been doing, but we're doing it twice. Now, I'm going to hold off on B for a second. Actually, you know what? Let's just go through it. For number B, or for letter B, I got two equations. I got equation A, and I've got equation B. Right away, what do we notice about these two lines?
The slope is the same.
The slope is the same. Colby, what does it mean if my slopes are the same? What type of lines are we going to have?
Oh, they're parallel?
Parallel.
Yeah.
Let's see. For line A, my M is 1, my B is 3. So if I'm going to graph this line, what do I do first? Make a point at 3 on the y-axis. And then I'm going to rise and run what? 1 and 1. Up 1 over 1, up 1 over 1, up 1 over 1, down 1 left 1, down 1 left 1, all the way down. Again with our ruler, we're going to line those dots up. And I'll label that line A. Sound good? What's my slope for line B? 1. What's my y-intercept?
-3.
-3. So I'm going to begin by making a dot at -3. And I'm going to rise 1, run 1, rise 1, run 1, all the way up and all the way back. With our ruler, we draw a line through all those points, and we'll label this line with a lowercase b. Now, when we graph these two lines, what are we looking for again? We're looking for the point of intersection. Where do these two lines intersect? They don't. Will they ever? No. That's literally the definition of parallel lines. Two lines that never intersect. So if we're asked to find the solution, what do you think our answer here is going to be? No solution. I love that you said undefined, Gurpreet. We're going to stick with no solution, though. No solution. Undefined is one of those weird math terms. It's kind of hard to explain. The fact that there is no solution means that we've defined technically a solution. It's just the lack of solution. Undefined is a whole separate idea that we're not going to get into because it doesn't matter here. But technically, we did define a solution. There was just no solution. All right? Sound good on B?
Yeah.
Okay. What do you notice about C? What's weird about C? It's in standard form. The first one is, what's going on with the second one? Christian?
There's a 4 in front of the y.
There's a 4 in front of the Y, and there's a 12 on the right. It's just all jumbled up. Do we know how to convert these into slope-intercept form?
Yes.
Okay, go ahead and do it. You got a lot of space down here. Underneath your graph, take a moment and convert A and B into standard form for me. Oh, sorry, slope-intercept form. But you knew what I meant. Give me a second.
What happened to the past?
Go ahead. It did. All right, let's take a look at this real quick. I want to make sure we're all on the same page because this one is weird. For my orange equation, equation A, what can I do to put this in slope-intercept form? What can I do first? Subtract the x. Okay. I get 2y equals negative x plus 6. What can I do now with my, Colby?
Divide by 2.
Divide by 2. And I get y is equal to negative 1/2 x plus 3. Negative 1/2 x plus 3. Did I mess this up? Pretty sure I did. Dang it. Okay, for B, what do I have to do on equation B? We'll subtract 12. We want y by itself, right?
Oh, yeah.
So 6x minus 12 equals 4y. I did mess this up. What do I do now? Divide by 4. So y is equal to 3 over 2x minus 3.
Subtract.
Did I do that right?
Yeah.
Wait.
No?
Meant to be.
I got negative.
No, because wait.
It looks right to me.
I got negative 3 over 2 plus.
Hold on.
Equals negative y?
Oh, that's what I did.
Wait, so it's not 4.
Wait, you divide by negative
So I
3x.
added 4y.
Yeah.
plus the
No,
4y,
because
you
I
minus the
see
6x, and you divide by 4. Interesting.
Because I
What did I do?
I got plus 2.
I converted it to negative. Yeah. Oh, wait.
Oh, I'm tripping.
Oh yeah, it would be negative 4y.
Yeah. You're right. Yeah, Judy, you got it. And Colby, thank you.
Good job, dude.
The 4y should have been negative. My bad. So negative 3 over 2x plus 3. Thank you. Good catch.
Yeah.
All right. This is not what I wanted this equation to be, but whatever. If I go here to 3, down 1 over 2. Do these two even intersect? They do?
At 3.
They do like the y.
Oh, yeah. Dang it. Okay, stay with me, please, guys. Did I mess that up too? Oh. Can't even see what I'm doing. All right, so what will my solution here be? Alex, what do we got?
0, 3.
Good. How did I do that? Oh, it was supposed to be 3x. Dang. Oh well. So I messed it. I mean, this example ended up working out. This was supposed to be an example of. Let's not worry about it. Unless. Okay, if. Sorry, I'm all over the place. The x was supposed to have a 3 in front. And basically what you would have got when you worked through this is you would have got a and b being the exact same equation. Okay? So if I graph the same equation and the two lines are like on top of each other, right? How many solutions do you think that would be?
Infinite.
Infinitely many.
Wait, what? What happened?
Here, go ahead and flip over. We could just write this one in. Mr. Church, what? Oh. Okay. Okay, do your best to draw a little makeshift graph.
What are they called?
What?
It's called what?
A makeshift graph? As in like janky? So in this example, what do we notice about the two equations?
They're the same.
They're the same. Great observation, Christian. I appreciate that. They are the same, which means they have the same slope and they have the same y-intercept. So if I was going to graph these, up 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. Here's equation A. For equation B, I plot my y-intercept at 2. I go up 2 over 1, down 2, left 1, down 2, left 1, down 2, left 1. And like Christian said, they're the same equation. Well, what do we notice about the lines?
They're on top of each other.
They're on top of each other. They're the same line. Do you guys see at any point where these two lines intersect? Yeah? Go ahead and point to it. Where do they intersect?
Everywhere.
Everywhere. Are they ever not going to intersect?
No.
No. So what would my solution be to this equation? Infinitely, I always spell this wrong. Infinitely many solutions. Yeah, it's the same thing like we did with equations. Either one solution, many solutions, or no solutions. It's the same thing here with these systems of equations. We can have one solution, like we did right here and right there. We could have no solution, parallel lines. Or we could have infinitely many solutions. They're the same line. Right? Because we're looking for the point of intersection. They either intersect at one point, intersect at no points, or intersect at all the points. It's the only options we have. How's that sound? Okay?
Fine.
That's what the last example was supposed to look like, but I messed it up. I was too busy making goggles.